vectoring matrix constructors provide convenience in initializing both vectors and matrices with the corresponding component values. And we just discussed this idea of combining 3-component vector with the 4-component vector constructor to initialize a vector of 4 components. If there's a single value provided to the matrix constructor, then it's used to initialize all components of that matrix diagonally, while other elements are set to 0. So matrix transformation is an extension of GLM. I would say it's an extension of GLSL. And this is also an example from GLM manual. So here we create our position, which again is set to be the origin of the system of coordinates. So let's illustrate this. We can take the initial position right here. So this is our position right in the origin. Then we construct a model which creates an identity matrix. Right? So our model is 4x4 matrix. And this is an identity matrix. That's the constructor. And then we populate the last column with values 1, 1, and 1 in this convenient constructor for 3-component vector. So there will be values 1, 1, 1. The rest of the matrix is set to 0. And of course, if we calculate where is the position of 1, 1, 1, so it's like this. If this is 1 unit, right, 1 unit and 1 unit this way as well. So this basically will be somewhere over here. There's a new position, and when we take this position and multiply it by this matrix, which is of course translation matrix, so it moves this point to the new location. So the new location of our position will be updated, and this position is called transformed. So this will be the new vector, which will have new XYZ position 1, 1, 1. So this is 0, 0, 0, and this becomes 1, 1, 1. Right, those are the coordinates. In almost all cases, we begin creation of our matrices by using the identity matrix. So typically you would create an identity matrix and then make some updates to it to make it look like a translation or rotation or scale matrix. And so there are a couple of constructors that do that. If you specify value 1 to the matrix 4x4 constructor, which takes this initial value, of course it will construct the identity matrix. And as I have shown you before, the default constructor is also constructing an identity matrix. So this will be also constructing an identity. So these are 3 helper functions available in GLM library through this header matrix transform.hpp, and they are rotate, scale, and translate. So we have in our GL262 labs, we have a subfolder named example, and here we have lecture 13 matrix, which is a demonstration of these transformation functions in GLM. So let's open this project. Just first go to build and clean my current solution, then file, close my solution, then file, open. And under GL262 labs we have example. Just navigate to lecture 13 and open this solution, lecture 13 matrix. Alright, so let's build this solution. If you're loading this project the first time, it will be asking you to update to the latest version of your compiler. So you just say OK to that dialog box, and then you can build. So we can try running this example. So we can go debug, start without debugging, and this creates this animation of a flagging figure in line drawing mode. So let's slow down this animation a little bit and see what kind of transformations we can identify in the code. So let's open the code, Solution Explorer. There's only one source file. So here we have our matrices, 4x4 matrices for a rotation around the y-axis. There's a translation matrix, and there's also scaling matrix. And all three of these matrices are initialized to be an identity matrix to begin with. We also have the combination of these matrices apparently that we're going to produce, which will be the model matrix. We also have the view matrix, and we also have a projection matrix or perspective matrix. We also have a theta angle that generates a little bit of animation with every frame that we display on the screen. And we also have a scaling amount that we use to change the size of our model. And as you remember, this is where we create this perspective by calling GLM perspective helper function, specifying that this is our 60-degree field of view angle. Then this is the aspect of our window display, assuming that both width and height of the window is the same. And then there's the near plane and the far plane of the frustum of view. I'll skip over to the rendering function. So these are functions that deal with shaders. And now here's the render function, which is invoked for every animation frame that we display to create this animation. And so here we increment our theta angle of rotation around the y-axis, and our increment is 0.01. So if we want to slow it down a little bit, we can add another 0 in the middle, so it becomes 0.001. So then we say that for our flag model that we are currently loading to display, the scaling amount is making it 10 times smaller, so it's 0.1. And here's the application of these functions. So first we construct the scaling matrix, and we begin with identity matrix, and we use this scale amount on all three dimensions. We produce a vector of 3 elements which will be specified for scaling of x, y, and z, and we name it matrix scale. So then we want to do some rotation, and the rotation is using this theta degree. And again we use the identity matrix to create our rotations. Now this vector, if you can see, this is vector 3, is specifying that, so this is the axis of rotation, which is the vector in the direction of y-axis, and this is the angle to rotate it by. And of course the theta angle is incremented a little bit, and this is specified in radians. So this is our rotation, and it's going to be happening like this. You already saw that we rotate around the y-axis. And then also our translation moves the object from its original position. We'll move it down 0.25 units, and then we also move it -2 units in a negative direction along the z-axis. So we end up having our model somewhere here, and so we're starting to rotate it. So notice that we multiply all matrices together by generating the model matrix, right? So this is our model matrix. So it incorporates scaling, then rotation, then translation. So this is why the actual application of this transformation is that first, this is the original size of the object. And I believe we're scaling it by this amount, so it becomes smaller, like 10 times smaller. Then we do the rotation. Right, so then we do the rotation of the object, and then we translate it 2 units back. Right, so this thing, after being rotated, it gets back over here. So now the next thing is that we specify matrices as uniform variables in our shaders, and those are model matrix, view transformation or camera transformation, and then the perspective. Notice that we're using polygon mode lines, and we want to draw both front and back versions of our triangles. So that's why our figure appears to be like see-through. Then we draw the triangles. We swap the buffers, which makes the next frame visible, and post-redisplay call into GLOT makes a request to create new frame of animation when the graphics hardware already done painting the current frame. So this makes it a continuous animation. So let's run this again, but this time it's going to be a little bit slower because I made my update and changed the rotation increment 10 times smaller. Alright, so now it's rotating a little bit slower. So this is our quick demonstration of these helper functions to generate transformation matrices, scale, rotate, and translate, and then we combine all three of them into our model matrix, which applies all of these transformations together.